Lesson 3.4, day 1. Right now, students are working on the warm-up of just setting up the constraints and objective equation only. They do not need to graph or solve. I'm going to give them about 1 more minute. There's a little tricky thing with this one. All right, I'm going to start reading through this one. There's a lot going on here. So Bob makes burgers in Prairie du Chien for the big summer crowds. He needs to make at least 45 burgers before he opens so that they are ready to fry. He makes special mixed burgers and regular burgers, but only has at most 20 minutes to get ready. If he can make 3 regular burgers per minute and 2 special mixed burgers per minute, he needs to make some quick decisions to get ready for his day. So, of course, he would have time to set up these constraints and objective equation and quick solve this to figure out how many of each type he can make before he gets to work. Bob really wants to maximize his profits today, and he makes $2.60 per regular burger and $3 for a special mixed burger. How many of each type of burger should Bob make? Okay, so right here, the how many that they're asking us to find, that gives us a hint to what we need to set up for our variables. So I just used R as a number of regular burgers. S as the number of specialty burgers. Okay, so it says set up constraints and objective equation only. Don't solve. So do my constraints over here. And I'll do my objective over here. I personally like to do my objective first. Okay, remember, your objective is the one you're trying to maximize or minimize. So when it says he wants to maximize his profits, his sales, that's going to be my objective equation. So I'm going to use a capital P to represent his profit here. And we get $2.60 for every regular burger. So my number of regular burgers, which is R, times 260. That would give me how much I profit off of that burger. $3 for every specialty burger. Well, S is my number of specialty burgers. So if I total that with 3S, that's my objective. That's what I'm trying to find the maximum of. Okay? Not always, but usually that one is dealing with money because you're usually looking to like maximize your profit or like minimize your costs. Okay? All right, now the constraints here. So now I have to kind of look at like our restrictions. So I go back up into the word problem and I kind of start dissecting it as I see he needs to make at least 45 burgers. Okay, so no matter how many regular and how many specialty, I need to make a total of at least greater than or equal to 45. There's my first constraint. All right, here's the tricky part, the one about the minutes. So he only has 20 minutes to get ready, and he can make 3 regular burgers per minute and 2 burgers, the specialty ones per minute. Now, it's not this. This is what a lot of people would think. Don't write this down. Because now you're taking 3 burgers per minute times your number of burgers, and we're trying to get like in units of minutes. Nick, something you want to add here?
Yeah, you gotta do the reciprocal.
Yeah, you kind of basically have to like find how many like minutes it takes to make 1 burger, right? So yeah, you're right, the reciprocal here. You can think of it like this. It takes us 1 minute to make 3 burgers. Or another way to think of it, it takes us like a third of a minute to make just 1, and that's my number of burgers. Okay, that's the tricky part about this one, so I want to do it together. Third of a minute times your number of burgers of the regular burgers. Okay. For every 1 minute, I can make 2 specialty burgers. So that one, it takes me a half a minute to make just 1. So the half a minute times my number of specialty burgers, that has to be less than or equal to 20 minutes. Okay, that's kind of the tricky part, is taking those rates and applying them to the constraints. All right, the only other constraints I would have here is that my number of burgers has to be positive. Those are kind of like those silly ones that a lot of people forget about. But I obviously can't have negative number of burgers. All right. Good stuff. That's review from 3.3. Oh, also, this is the last lesson in chapter 3 already. Craziness, right? This is a really short chapter. So I mentioned we have a mini quiz Tuesday. Right now I'm planning the chapter 3 test for next Friday. Give us some like review days. This is a 2-day lesson. We'll finish this up Monday. Maybe we can talk more about the test next week, but this is the last lesson. And, oh my gosh, this is one of my favorite things from semester 1. Seriously. We're going to solve systems of equations, just like we did before, but now we're going to have 3 variables, 3 equations. So they're going to look like this. Instead of just x and y and having 2 equations, we have x, y, and z, and we have 3 equations. Yeah, you guys, that's what we're going to do. Okay, first of all, let's conceptually understand what we're doing before we jump right into the algebra. So, you guys talk about planes in geometry, right? Points, lines, and planes. We talk about that a lot. So, when I have an equation in 3 variables, it's on a 3-dimensional plane. It forms a plane, okay? And when I was in college, and if you ever get to the point in your career, if you want to be like an engineer or something, you have to take calculus 3, you will actually graph something in a 3-dimensional plane. It's called like an X, Y, Z axis, and you graph in like a 3-dimensional plane. Okay? Don't worry, we're not going to do that here. All you have to know is we're basically solving system meaning more than 1 equation, of 3 variables, and these 3 variables form planes. Okay? So just like before, when I had 2 dimensions and they formed a line, I was looking for their intersection point. Now I have instead 3 planes, and I'm looking for where they intersect. Okay? So they intersect at what we call an ordered triple, x, y, and z. And again, this is what it would look like if you were to graph this on a 3-dimensional plane. So something like this, if you can picture, you have 3 planes that intersect. You see how they're kind of like intersecting at that little point that I put in your notes right there? This is my one solution to the 3-variable system. It would intersect at some point x, comma, y, comma, z. We call that an ordered triple. So basically, it's just like solving 2-variable systems, but it's like more steps. Now you have to solve for all 3 variables instead of just 2. Okay? Now, just like before, when I was solving these, I could have, if I had 2-dimensional, I could have infinitely many solutions if the 2 lines lied right on top of each other. Okay? So look at my 3 pieces of paper here. If these are my 3 planes, and they all line on top of each other, I'd have infinitely many points where they intersect, right? Or another way is maybe the three planes intersect in a line. Okay, and you guys know from geometry, when you have two planes that intersect, they always form a line. So I could have three planes that intersect, and I have all these points where the planes intersect. This is infinitely many solutions. If they intersect in a line, or like I said, all three planes could be lying on top of each other. Okay, then kind of my third case scenario here, all these ones, if I just had like three pieces of paper kind of floating right here, okay, these planes go on forever in the directions, but are they ever going to intersect each other? No. Here they intersect each other, but do those three planes have a common point of intersection? No. Here, they all intersect the red plane, but again, do they have one common intersection point? No. So we could also have no solution to these systems, just like before. This is possible in our three-dimensional plane, that they have no common intersection points. Okay. So, you guys all know how to do substitution and elimination. You showed me that on the quiz. And it's just like substitution and elimination, double, times 2.
Yeah.
Here's the good news. You know how in 3.1 you have to solve by graphing? These you don't have to solve by graphing, okay?
Oh, thank the Lord.
You're never gonna have to graph on a three-dimensional plane unless you take Calc 3 in your life. Don't quote me on that. Maybe you will. I don't know. But that was the only time I had to as a math major. So, we're not gonna graph them. We're only gonna solve these algebraically. Here's my other good news for you. I'm gonna show you both ways today. We're going to do the first one using elimination because I personally think elimination is easier with these. And then I'm going to show you substitution. And then from here on out, you get to decide which method you use for the three variable ones. Okay? You know how on the quiz I said, hey, use substitution for this one, use elimination for this one? Anytime you're assessed on the three variable, you're going to get to decide. Okay? But
4 variable ones too?
Not in this class.
Yeah.
We're not pre-calc.
Nope. Okay. So we're going to do elimination first because, like I said, I personally think it's easier and usually students like that method better. All right, so the first thing you have to decide is what variable you want to eliminate, and you have to eliminate it from all three equations. All right, if you have colored pens, it's kind of helpful. I'm going to kind of color coordinate these. You can call this equation 1, equation 2, equation 3 if you want. I'm going to call this one blue, this one red, and this one green. Okay, so just like before with elimination, we kind of look at the coefficients on the variables. And I'm like, okay, the x's, they all have even numbers, but, 6 and 4 are kind of big numbers. I look at the y, I'm like, ooh, 2, negative y, negative 3. Those are pretty small numbers. Some are positive, some are negative. And then the z's are all positive, and they're kind of big numbers. So I'm going to eliminate y. Okay, so I kind of broke it down for you step by step. So the first step is we want to rewrite each system into variables, aka eliminate a chosen variable. So we're going to eliminate y, and you have to eliminate it from all three, but here's the kicker. You can only add 2 equations at one time. Okay, so let's say I'm going to use the blue equation first. Look at my green equation. What could I multiply my green equation by so that when I set up my elimination, it would eliminate with my blue? 2, right? So this is a great place to start. If I times this by 2, and we got to do this, just like before, we have to multiply everything by 2, all 4 of those terms by 2. I'm going to write it down here. I get 12x minus 2y plus 8z equals negative 6. Now, my best advice to you is do these problems slowly, because if you make one small mistake by just like a simple multiplying, everything else can be wrong. And these problems get really annoying to try and find your mistake, okay? All right, so I changed my green equation, and now, just like before, I'm going to line up my variables. So I'm taking the blue equation, lining up the x's, lining up the y's, lining up the z's, lining up the equal signs, lining up the constants. And we do the elimination. So we add these together vertically, just like before. 12x plus 4x is 16x. My y's eliminate. That was my goal. 8z plus 3z is 11z. Negative 6 plus 12 is 6. All right, that's all the further I can go. So I have eliminated y from the blue equation and from the green equation. Which equation have I not eliminated it from yet? The red. Okay, so this is where I'm like, you have to do elimination kind of like double. So I need to eliminate y from the red equation yet. Now, obviously, since I need 2 equations in my elimination process, you're going to have to reuse one of them because there's only 3. It doesn't matter which one you reuse, okay? So me looking at this and like, hey, that green equation was pretty easy to work with. This time, what could I multiply my green equation by now if I wanted to eliminate it with the red equation? It would have to be negative 3 because we want to make it a positive 3, right? Okay. Now, if you don't want to erase it, you could just do this too. You could just say, all right, so for the first step, I did by 2. Now we're doing negative 3. All right, so I have negative 18x plus 3y, that was the goal, minus 12z equals positive 9. I could have used the blue equation to eliminate it with the red one. It doesn't matter. You get to decide that. What does matter is that you use each equation at least once in this first step, meaning you have to eliminate y from all 3. Here's a mistake students often do. They'll choose to eliminate y, and then they switch up. They're like, actually, I'm going to eliminate x of these other 2. You have to eliminate the same variable from all 3. And now you can see, using color coordination, I used all my equations at least once. Okay, one of them you're going to have to reuse because there's only 3. All right, so we get negative 16x. My y's eliminate. That was my goal. I get negative 7z, carry down the equal sign, and I get 2. Now, if you do this first step correctly, you should get 2 equations with 2 variables, the same 2 variables. And then you know how to solve it from there, right? 2 equations, 2 variables. That's what we did in 3.1. So picture this as almost like you have a new problem. I have 16x plus 11z equals 6. And I have negative 16x minus 7z equals 2. Now I picked a nice problem for us to do together as our first one. What happens to be really nice about this setup here, Cindy?
X crosses out.
This is already set up for elimination. That's not always going to happen, okay? You might get 5x plus 11z equals 6 and negative 16x minus 7z, and then you'd have to times them both by something, okay? This isn't always going to happen where they're set up already for elimination. In this case, I just wanted to kind of pick an easy one. This is already set up for elimination for us because this x's are opposites. So here I have 4z equals 8, and now I can solve for z. I like to circle variables after I solve for them. All right, so here's what I've done so far. I eliminated y, got my system down to 2 equations, 2 variables. Now, if you wanted to, some people like to do this. They do like elimination for the first step, and then once they get it down to 2 variables, like, man, this looks nice for substitution, and they switch up the method. You can do that too. You can do like a mixture of both. Okay? Once you get it down to here, solve it how you want it. All right, folks, now that I know what z is, what variable can I find next? X, right? Picture this. 2 equations, 2 variables. And this is a normal equation. You'd find x next. You could use either equation. I use the one with the positive 16. So we know 16x plus 11 z, we know z is 2. Okay, I'm just using this one. Equals 6. Now I can solve for x. Okay, I get x to be -1. So I'll say this again. This step, folks, this step you already know how to do. 2 equations, 2 variables. If you get 2 equations and one has x's and z's and the other has y's and z's, you did something wrong. They should have the same variables. All right, then our last step, similar to what we did here, now that we know x and z, we can use any of the 3 original and find y. Okay, let's use, which one did I use? I used the blue one. So I did 4x. So substitute and solve for the remaining variable. Plus 2y, y is what we're trying to solve, plus 3z is 12. Well, now we know z is 2. We know x is -1. Okay, let's do some math here. -4 plus 2y plus 6 equals 12. 2y plus 2 equals 12. Y is 5. Was that fun?
Yeah.
Okay, we're not done though. How we write our answer is exactly like how we used to write our answers as an ordered pair. Now we're writing it as an ordered triple. So ordered triple, how do I use red? Ordered triple, it goes in alphabetical order, just like ordered pairs goes x, comma y, and then z goes last. So our final answer would be -1, comma 5, comma 2. And you guys just found the point where those 3 planes intersect. Isn't that cool? You could check this just like you do with 2 variable systems. Plug it into each of the equations and it should work. Desmos does not graph in 3 variables. Okay, that wasn't too bad, right? That's elimination. If that made sense to you, that's good. That's usually the method people like. You can see, though, how one small mistake, like here, if I would have forgot to like multiply this -3 by a 2, that number I'm using in this step, which I'm using in this step, which I'm using in this step, will make everything wrong. So you just have to do it slow and be careful. I actually made a worksheet one time of like mistakes, and because students struggle to like find their own mistakes. So I made a worksheet of making a bunch of mistakes and made people practice finding mistakes. It's kind of fun. I should see if I still have it. They're like, no, we're good. Okay, now we're gonna do it using substitution. Okay, and I want you to be open-minded to this, because I sometimes do like to use substitution on word problems, because sometimes it's set up really nice for substitution. All right, look at my equations here. So I'll call this one my blue one again, the second one my red one, and the third one my green one. Why is this set up nicely for substitution? Which one? Which color? The green one. It's already solved for y. Okay? So we're going to substitute y. So just like the last example, you basically just have to do this double. So you have to substitute it into the blue equation and into the red equation. Okay? So you choose one variable and one of the equations to solve for, get by itself. That's already done for us. Again, it's not always going to be like that. I'm just picking easy examples to start. So this one's solved for y. I would also recommend, if you're somebody like me who writes your 2's like this, to put dashes through your z's, because sometimes people get their z's and 2's confused. Okay, if you write your 2's like this, you should be good. All right. So choose one variable to solve for, get by itself. Substitute into other 2 equations. All right, so I'm just going to do the blue one first. So we have 2x plus y plus z equals 8. Okay, this is what we're substituting in. X plus z. All right, there's nothing to distribute here. I do still, get in the habit of putting it in parentheses anytime I'm substituting, so we can clean this up a little bit. We have 3x plus 2z equals 8. Can't go any further. All right, so I have to do this double. So I have to substitute it into the red one. That one is negative x plus 3, and I'm substituting the same thing, y minus 2z equals 3. Substituting in. X plus z. Okay, here I have a 3 outside that I would need to distribute. So, cleaning this one up, I have 3x plus 3z minus 2z equals 3. I end up having 2x plus 1z equals 3. Okay, so again, you should get 2 equations with the same 2 variables. Do we have that here? Yeah, I have 2 equations with x and z. All right, so from here, step 2, you guys know how to do this. If it helps you to rewrite it and just like ignore the top part, you're like, hey, I know how to do this. I'm going to keep going with the substitution process. So I'm going to write them side by side like this. Like, okay, I'm going to separate them. I'm going to keep going with elimination. If you wanted, or I'm sorry, keep going with substitution. If you wanted to change and, hey, now I'm going to use elimination, you could do that. But this one's set up nice for substitution. I can solve this for z. Z is 3 minus 2x. So I come over here, take out the z, substitute in 3 minus 2x. And then I can find x. All right, I get x to be negative 2. Careful with all that algebra. Sometimes, too, students like to do this. They like to set up a little template for their final answer. And then as they find answers, like, okay, x is negative 2, they kind of just like to plug it in. And that kind of helps them, too. Okay, now I got to find y, now I got to find z. Which variable can I find next? Z, right? Sorry, thank you for raising your hand so politely. Z. Nice thing about substitution is you have these nifty little equations to plug things back into. Z is the same as 3 minus 2x, and x is negative 2. So z is 3 plus 4, 7. Z is 7. Okay, now, y, and this is one of our original equations, y is the same as x plus z. So if x is negative 2, and z is 7, y is 5. That right there would be your final answer. That ordered triple. Pretty cool, huh?
I didn't say that.
That was better than I thought it would be, honestly.
Yeah.
Not bad.
All right. I know this is very new to you, but just out of curiosity, how many of you think you like the elimination better? All right, substitution.
If they set up like that, then I'll like substitute.
Well, yeah.
But
Yeah.
Kayla, what question did you have?
How did you solve for the third one?
Why?
Yeah.
Look right here.
You don't have to see.
Y is the same as x plus z. Now we know x and z, so that'd be 5.
You plugged the 2 variables you already found into your original equation.
All right, we have a few minutes left, so what I'm going to do, if you flip over your note packet, there's one problem that you get to try. You can decide. Substitution.
There's two problems.
Just do the top one, sorry.
On your own.
Example, yeah, the one that says on your own. Example 3, we'll save that for Monday. All right, try this one. You can use elimination. You can use substitution. You can eliminate X. You can eliminate Z. You can substitute for Y. You decide. I'm going to put the answer on the board. That way, for the first variable you solve, if you get it wrong, you don't go any further. This is what I got. Okay. Give it a whirl. Yep, so now you gotta eliminate X from this one. Yep, you get to pick. I'd probably do this one. Is that the easy one with not over? Yeah. Do you want to eliminate it with this one? That made it 2X. We want to make it like eliminate with that. Negative. Because you're trying to eliminate the X, right? Yep. And you already did it from these two. Here, right? So now you eliminate from this one. You need to pick which one you want to eliminate it with. So I would use this one instead of 1 in front, use this one instead of -3. Yep. You go fast, so these are going to be eliminating X.
Yeah.
Times this one by -3.
Yeah.
-12. Looks good. And then you times this one by -2.
Yeah, it's on this one.
-2 minus 2 is -8. That should be +7.
Yep.
It's as small as that, and it can ruin everything. Beautiful. Okay, so now treat it as like I have 2 equations, 2 variables, so you have to like eliminate, like, and you can like rewrite them on top of each other and like do the whole process over again, like eliminate something. Oh, okay. Yep. Okay, we're gonna leave off the video here. Just try this problem on your own. That's the order triple you should get. And we'll pick up this lesson on Monday.